right. Thanks everyone for joining us today. It is my pleasure to introduce Justyna Signerska-Rynkowska. Justyna is an assistant professor in the Department of Applied Physics and Mathematics at Gdank University of Technology. And her research focuses on dynamical system theory, chaos theory, and applications to modeling of biological phenomena, especially to neurosciences. So today she will share with us some of her related work about type 3 dynamics and beyond in shaping responses to transient inputs in hybrid neural models.
Thank you. Thank you for the invitation and also for this very nice introduction. I'm somehow now double affiliated because I'm on the temporary from Gdańsk University of Technology, and now I work in the Dioscuri Center associated with Institute of Mathematics of the Polish Academy of Sciences. And I would like to present the results of my joint work with Jonathan Rubin and Jonathan Touboul. And also, if time lets, I would like to give you some insight on our future work, or the work that, let's say, we just have started and that is somehow connected to what will be the theme of my, the main theme of my talk. Okay. Okay, so for a moment I couldn't change the slide, but it works. So I'm going to speak rather about neuron firing properties as a response to transient inputs, but this is also connected with actually what type of class a neuron represents in terms of Hodgkin electrophysiological classification of neurons. So maybe let me very briefly recall this classification. So this classification, it's rather with respect to sustained inputs, and in this case we can distinguish type 1 and type 2 neurons, which both fire repeatedly when the excitation level of the sustained input is high enough, but they differ in their frequency amplitude curves, meaning that roughly speaking, for this type 1 neurons, this frequency amplitude curve is continuous. So for example, if the neuron is stimulated with some relatively small excitation level, it will respond with very, very small frequency, yes? On the other hand, these type 2 neurons, they cannot maintain very low frequency response. Once they respond, they, let's say, respond with some, so either they are silent or they start responding, but once they respond with a frequency that is not necessarily small, yes? So for example, on this frequency amplitude curve, this would correspond to some jumps or some discontinuity. Many studies were devoted to this type 1 and type 2 neurons, in particular in models. As I am a mathematician, I mainly work with models, yes? These type 1 and type 2 properties, they can be linked with bifurcation properties. So if, for example, when the onset of firing occurs via saddle node on invariant cycle bifurcation, this is going to correspond to type 1, yes? On the other hand, when firing occurs because a limit cycle is born via Andronov-Hopf bifurcation, this would rather correspond to type 2 neurons as the this limit cycle appears with some, let's say, prescribed periods or some prescribed frequency. But one can also distinguish the third class of neurons, so-called type 3 neurons. I've came across the opinion that this is the least studied class of neurons, but it is also quite common biologically. Let's say type 3 neurons are those neurons that may exhibit that no matter how strong there is this sustained excitatory input current applied, they will fire at most a few spikes. Yes, so and then there will be a silence. So this is some how we can think about this. In some settings, actually these type 3 properties, they can play a role, they can be advantageous. So for example, in situations when every single spike carries some information, or when there is very rapid stream of stimulus and neurons needs to somehow respond selectively to it. Yes, so I already used this word. These type 3 excitability properties are connected with some sort of selectivity, yes? So the neurons, they fire more selectively to some inputs, let's say. And it can be also linked with the following properties. So post-inhibitory facilitation and slope detection. These are the two properties that are connected with neurons' responses to transient inputs. And these are the two I'm going to talk about. But also it can be connected with phase locking, or rather something like phase locking precision. So we can think about it that for periodic input, so there is some sustained periodic input, a neuron fires some prescribed number of spikes per each cycle, but also these spikes, they occurred only at certain phases of cycles, so like only in some bounded range of phases within each cycle, or even prescribed phases. And the other feature is coincidence detection, which says that, for example, if there are 2 or even more inputs coming to the neuron, then a neuron will spike if these 2 inputs, if they overlap enough, so if they occur close enough to each other in time, yes. So about phase locking and coincidence detection, maybe I will mention something at the end, and I will, as I said, I will speak mostly about post-inhibitory facilitation and slope detection, but I think that we will, in a moment, we will have the opportunity to take a closer look at this definition. So maybe let me now skip this. Okay, so we mentioned that this type 1 and type 2 excitability properties are connected with the types of bifurcation the model undergoes, but on the other hand, this type 3 behavior is associated with the existence of a stable fixed point, yes, at resting voltage that persists for all level of inputs. So when this stable fixed point corresponding to a resting state persists for all levels of inputs, we say that this is like pure type 3 responsiveness. However, as was shown in our recent paper, to display this post-inhibitory facilitation and slow detection, a neuron does not need to be a pure type 3, by which we mean that we allow this stable fixed point to actually be lost or lose its stability as input increases. Yes, of course, it needs to persist for some certain interval of input levels, but it is also allowed to in general, it is allowed to disappear, to lose stability, yes, when the input is high enough, let's say. So we address this question, this problem, by using a planar hybrid model, which I think is now well accepted, well recognized model. So now let's have a look at the subthreshold dynamics of this model, which is described by this system of differential equations. Yes, so we have the equation for the voltage, for the membrane voltage, and the equation for the recovery variable. Yes, so this W variable. I is the input current. So in our approach, it can vary in time, and it can include both positive, so let's say excitatory parts, as well as negative, so inhibitory parts. And we need to, of course, we need to make some assumptions. Yes, we try to be as general as possible, but obviously some assumptions need to be made. So these B and C are positive and non-negative parameters, respectively. We also allow C equals 0, in which case the W null is vertical, yes, with respect to the it is vertical. About this function f, we assume that it is smooth enough, let's say C3. It's convex and such that it has negative derivative, at least for small enough values of v. It reaches its global minimum at some point, let's say VF, WF, and also for large values, it is positive and it increases fast enough so that the following integral actually converges. So this assumption is needed to assure that for some initial conditions, the membrane voltage will blow up. I mean, it will go to infinity in finite time. So this is because this is how we defined a spike in this model. And I will speak in a moment about spiking and resetting mechanism. But let me just mention that with these assumptions on the function f, we actually include the Izikevich model, the exponential Brett-Gerstner model, adaptive exponential, and the quartic model, which we used actually for our numerical illustrations. Okay, just for completeness, yes. So a similar model, usually with constant input, was studied in number of works. In particular, I think Jonathan made in 2018 the detailed analysis, yes, of the subthreshold dynamics, the bifurcation diagram that we see here. So the bifurcation diagram with respect to I and B. So this is yes, in general, we can think that this model dates back to Izikevich. So let me go back to spiking, which are already mentioned. So, okay, I said that in this model we define spiking as, well, firing a spike means that a voltage blows up. Yes, it goes to infinity, it's some finite type. But then we can ask what happens with the recovery variable. So we actually defined it that just after the spike, the voltage is reset to some resting value, but the recovery variable, it is incremented, yes, by some constant, which is another parameter in the model. So of course, for this resetting mechanism to be well defined, you need to assure that once voltage blows up, the recovery variable stays finite, yes. So for this, you need the additional assumption, the function f, that it goes to infinity, for v going to infinity faster than quadratic function. But actually, in our problem, yes, we will only consider whether a neuron fired a spike or whether it did not fire a spike. So we don't really need to care what happens after spiking. So the details of this resetting mechanism are not, they are not important for us. They are not involved in the proof. So actually we don't need to include this assumption. Okay, so I only mentioned that we have already two other works, yes, devoted to this model, which are included here. And in these works, yes, we really take we really care about the hybrid nature of the model, so we care about spiking mechanism. But here we don't need to take into account the details of this resetting mechanism. So, but on the other hand, we still need another assumption. So we assume that when actually there is no input, then on the left branch of the V nuclein, our system has a single critical point, which we denote by V star W star, and it will appear. So I include this notation here, and this for I equals 0, this point is asymptotically stable. So moreover, for each non-negative input level, our system does not have a stable periodic orbit. So this is a sort of technical assumption that is actually, it is not that it is completely necessary. I mean, you can also demonstrate, for example, post-inhibitory facilitation when this assumption is not satisfied, but it will just it just makes the proof more complicated. Yes, if I will have time, I will mention something about that. So let's bear in mind this assumption, yes, that the system does not support a stable periodic orbit. Okay, so what is post-inhibitory facilitation? So this, we have some qualitative definition here. So imagine we have a, let's say, a silent neuron, and this silent neuron receives some certain excitatory input, but this input does not induce a spike in this neuron. However, if it happens that the same input may actually cause a spike when it is applied after some preliminary inhibition, and if this excitation is applied with some proper delay after this inhibition, and if its duration is also not too, let's say, not it's also within some proper range of values, then we can say that then if this condition is satisfied and neuron fires, although it was not able to fire when it was just presented only the excitation, then we can say that a neuron exhibits post-inhibitory facilitation. So at the first glance, this definition may not seem so so simple. So let me just maybe comment that indeed it says that including this inhibition is necessary, but also this inhibition has a sort of like, well, it has facilitative role, yes, for a spike to be fired. So hence the name post-inhibitory facilitation. However, it's also different than the other notion used in literature like post-inhibitory rebound. I think this is how it is called. So in post-inhibitory rebound, a neuron fires the spike once the inhibition is, well, after the inhibition. Yes, here we require that, okay, the neuron does not fire only if only the inhibition is applied. So application of the excitation is also crucial. And also there are some constraints on the level of this excitation and the time delay between removing of inhibition and applying the excitation. Yes, and also the duration of excitation cannot be too short. So somehow to address this this issue mathematically, we consider our system with piecewise constant input that is actually composed of inhibitory phase, a resting phase, and excitation phase, and also actually the third phase, which is usually there is also the fourth phase, the silent phase, yes, the resting phase after removing of excitation. So maybe let us have a look at this picture. So the trajectories of our system when it is stimulated with this piecewise constant stimulus, they would be like concatenation of trajectories corresponding to autonomous system with given values of constant stimulus. So we have the initial segment, the orange segment, which is here. Yes. So let's start. Let's assume we start at this fixed point, V star, W star. So we have a system. Part of the trajectory that corresponds to inhibition. Then we have this blue segment. So actually here on the picture, we just see two segments, yes? The blue segment that corresponds to the zero input level after removing of the inhibition. And actually we can imagine, yes, that somewhere here there appears on this blue curve, there appears the third part of the trajectory, so a third segment which is defined for the excitation. Yes, but in our proofs, what is important, it is actually the location of these curves consisting of these two parts with respect to so-called firing threshold curve. So that's why I depicted this trajectory here. But before we will go to that, so maybe let us look at the post-inhibitory facilitation illustrated graphically, yes, with the numerical experiment. Okay, so we took the quartic model. We started with the initial condition 0, 0, which is the stable resting state, stable fixed point corresponding to 0 input level, we applied some prescribed level of inhibition for some prescribed duration of time. Yes, and then we applied some excitation with some fixed level, but we applied it after the TE time, after removing the inhibition, and we kept it for delta, yes? And we checked whether a neuron fired or whether it didn't fire. So, so here in panel A, we see how this firing is reflected with the parameter values of TE and delta and the duration of the excitation. Yes, and indeed we see that for some after let's say delta long enough, the excitation needs to be applied with some proper delay. Yes, that is neither too short, neither too long. This is also depicted on this three-dimensional picture. Yes, so we have red trajectories corresponding to spiking and black trajectories, black non-spiking trajectories, and so they are labeled with different values of TE parameter. Yes, and we also by colors we see the time course of the excitation and inhibition. Yes. So on this lower C panel, we choose some. We also fixed some duration of the excitation, and we varied only this TE parameter, so the time delay between removing of inhibition and application of excitation. So indeed, when this time delay was too short, as happens on C1, or when it was too long, as happens on C3, the spike was not fired. However, when this delay was within some proper bounded range of values, then indeed the spike was fired. I already mentioned, yes, that this post-inhibitory facilitation property is connected actually with the location of this concatenated curve. Yes, so this curve here that I will note capital C with respect to the firing threshold curve. Okay, so firing threshold curve is actually a curve that separates initial conditions such that trajectory starting at this initial conditions blow up, so spike, from those that do not. So it is also connected with the notion of a voltage threshold. Yes, so a notion that was addressed by some other authors. Yes, in particular, there, for example, Brett and Płatkiewicz works that they have voltage threshold, which is also a dynamical variable, which is described by a differential equation in the model. Yes, so in our case, the voltage threshold is not maybe it's not given by a differential equation, but our firing threshold curve. Yes, it's it is a it's not constant value. Yes, it's indeed some curve, and the structure of this curve actually the shape of this curve actually depends on the configuration of the phase space of the subthreshold dynamics. Yes. So, for example, when C is greater than 0, our W nucline, okay, it intersects with the V nucline at this stable fixed point corresponding to resting state, but we also have a saddle fixed point, yes? And in this case, such as this upper right and lower left, when there is no unstable periodic orbit, the stable manifold of the saddle fixed point actually acts as a firing threshold curve. Yes, this is the separatrix. It separates the conditions, the initial conditions leading to spiking and those that do not spike, that actually convert to the resting state. Yes, so of course the shape of this curve, it can it again, yes, it can cross this nuclei and so on. So it also depends on the model, it depends on the parameters. And then there can be also the third situation in which there is unstable periodic orbit surrounding this stable fixed point. And in this case, this red curve, so this unstable periodic orbit, it acts as a separatrix. So this last case, it actually persists also when, I mean, it can be also present when C is 0. But when C is 0, so the W nucline is vertical, it is also possible that there is no such unstable. Okay, so so maybe let me just mention. So here, this red curve, yes, it acts as a this firing threshold curve, among others, because we have removed the possibility that there is some, some stable periodic orbit, yes, that in turn surrounds this unstable periodic orbit, yes. So, for example, here, this additional assumption that I mentioned the beginnings here, it interferes. So now imagine that C is 0. So we have this this stable resting fixed point, and there is no unstable periodic orbit surrounding it. So in this case, one can prove that there exists a trajectory that actually voltage along this trajectory, it goes to infinity, but in not infinite, in not infinite time. So there is a single trajectory, yes, that acts as a firing threshold curve, and numerically it can be approximated by asymptotic reverse. So this is the concept that was developed quite recently by Ledstone and Rubin. So probably I know I won't display the very the mathematical definition of this post-inhibitory facilitation, but we formulated a mathematical definition of this post-inhibitory facilitation because we wanted to have a rigorous proof that this property occurs in this model under this assumption and so on. So of course we needed to formulate a mathematical definition of PIF, but I think that I will probably skip that. I can always go back to it if there is some free time. Yes, so this is this definition actually. And in this definition, we captured, yes, this property of PIF, yes, that the application of excitatory inputs within a certain bounded range of magnitudes. It can induce a spike if and only if this excitation is introduced within an appropriate bounded time window after the offset of inhibition. And but on the other hand, if it is too weak, so if the input of the level of excitation is not enough, or if it comes too early or too late, or when it turns off too early, so when the duration delta of the excitation is not long enough, then a spike is not fired. And our mathematical definition, yes, it also captures the fact that the application of inhibition is crucial for allowing the spike to occur. So okay. So now we see that this concatenated trajectory C, its position with respect to the firing threshold curve corresponding to different levels of excitation. Yes, so okay, actually purple curve is not depicted here. It will be the lower curve that corresponds to the 0 excitation level. But for example, what we see here, we see the green line, which is the firing threshold curve for the excitation level 0.4, yes? And we see that this whole C curve is actually above this green line, yes? So for PIF, we want to apply excitation somewhere when we are on this part of this curve C. But as this whole curve is actually above this green line, then applying excitation at the level of 0.4 will not induce the spike, because we need to be below, yes, below the separatrix to be in the spiking zone, yes. On the other hand, also this red curve it can be like too strong excitation, because actually for PIF, what you need to apply the excitation somewhere when you are below the corresponding firing threshold curve. Yes, so we need to apply this excitation. For example, when we apply the excitation at the level of 0.7, then somewhere during the time when we are on this lower part, the lowermost part of C curve below the blue line, then we can demonstrate that actually this PIF occurs. So let's say that the reasonable choice for the excitation level to show post-inhibitory facilitation is 0.7. But of course, the other parameters also matter. So for example, here we see the role of this excitation level. So that's what I said, yes, that for example, if you apply the excitation that is too low, then okay, you want spike. We also see the role of this time delay between inhibition and excitation. So, okay, we decided that we choose the excitation level 0.7, but for example, if we immediately apply the excitation just after removing the inhibition, yes, so we are here and there won't be a spike. Yes, because when we start applying the excitation, we are above the blue curve. Yes, so we want spike. On the other hand, if excitation comes too late, then okay, for some time we were below the blue curve, but again we managed to cross it from the bottom to up, yes? So we are, once we, at the moment when we apply the excitation, we are already above the corresponding firing threshold curve. So there won't be a spike. On the other hand, for some intermediate choice of this time delay, like t=1, the spike can be initiated and it can really materialize. The other, I'm running out of time. The other picture shows the role of the duration. Yes. So again, if the duration of excitation is too short, which means that we remove the excitation too fast, then actually the spike, again, it won't be fired, because at the moment when we remove the excitation, we go back to the 0 excitation level, so no excitation. And although we cross the blue curve that corresponds to the 0.7 excitation, we are still above this purple curve. This corresponds to the 0 excitation level. So, okay, so we want fire a spike, yes, because now we have 0, input 0, but we are above this separatrix corresponding to input 0. So let me just say that this PIF may seem as some, let's say, very specialized property, but although it seems a bit technical, it is not, because in fact, actually, it does not occur only for some very prescribed choice of this TE or delta values, but for some, or excitation level, but for some open intervals of set values. And in fact, the condition for PIV that the sufficient condition that we formulated here is that this whole curve, yes, if this bottom part of this concatenated curve, yes, if it remains bounded and if it remains in the basin of attraction of this stable resting fixed point V star W star, then PIF occurs for the system with this choice of inhibition and duration of inhibition. Yes, because okay, at the beginning we choose inhibition and duration of this inhibition, and so this is how we define this curve C. Yes, and then we remove inhibition and we have this lower part of this curve. So I think that the condition is quite simple. Yes. On the other hand, one can also consider the robustness of PIF, so which is, I think, depicted on these diagrams. So we actually indicated, yes, these intervals of delta and TE values that correspond to PIF with given either excitation level or a level of inhibition or the time interval, the time duration of inhibition. So the property which I think is maybe easier to capture is the slope detection. I mean, it's not necessarily easier to prove, but I think it's a bit easier to speak about it. Actually, I think it's less technical. So we say that a neuron displays slope detection if it does not fire when stimulated with too rapidly increasing or too slowly increasing continuous inputs. But actually, when this rate of change of input in some specific bounded range, then a neuron fires. Yes, so in this way, we can say that the neurons, when, for example, the slope is high, it means that it's large. It means that the amplitude of the stimulus rises quickly. Yes, or when the slope is low, actually the input rises slowly. Yes, and somehow the neurons actually does not fire to these two situations, but it fires in response to, let's say, some middle slopes. So we considered a neuron stimulated with tent-like input. So we have a continuous input, not like the previous one was piecewise constant, but not continuous. Here we have a continuous input in a form of some tent map. So there is some tent input and then silence. This tent map is described by this equation, which allows us easily to connect amplitude, slope, and the duration of this non-zero excitation. So the base of the tent. Yes. So if we fix amplitude, we have the following formula that relates and we vary the slope. We have the following formula for this time interval of non-zero excitation. So the duration of this excitation, let's say. And one can also easily calculate the total amount of current injected, which is given by this value. And we see that it is reversely proportional to the slope. Yes, so somehow a non-monotone dependence of response on input slope corresponds to non-monotone dependence on actually total injected current. So I think I need to. Okay, so again, let's have a look at the picture. Yes, so we took our model. Yes, we took some parameters and. We took this tent like input, we varied amplitude and slope, and we again recorded, yes, whether a neuron fired or didn't fire a spike. So here in panel L, we see this relation that between firing or non-firing and amplitude and slope. So amplitude needs to be large enough for a neuron to be able to fire. However, once it is large enough, we also see that there exists some range of low inputs and of small slopes and some range of large slopes for which a neuron does not fire, but it fires for intermediate range of these slopes. This is also depicted in this three-dimensional picture. Yes, we see again red spiking trajectories and black non-spiking trajectories, but also here on this lower C panel. Yes, so we choose amplitude, I think A equals 3, and we varied the slope. Yes, so for small slope or large slope, there was no spike, but indeed there was some spike for large slope. Yes, so here you for intermediate slope. So here you actually also see that, for example, a small slope means that there is this large duration of excitation. Yes, but it just changes slowly. On the other hand, for large slope, it means that the excitation is actually very brief. Yes, this time interval is very small. So I wanted to, so one can, how actually we can prove it. So of course I won't present a proof, but the heuristic idea behind the proof is that when our slope is small, we can actually think of this varying input as slowly varying bifurcation parameter. So we can, for each temporary level of input, we have depicted V nucline, yes, that this is this blue surface, and the W nucline, the red surface. At their intersection, there is this resting fixed point, yes. So it is indicated by this black curve. And now from purple to light green, we see the trajectories, yes, when corresponding to different slope values. So when slope is very small, actually the trajectory follows the fixed point, yes, then it starts slowly increasing, and actually at some point, this is indicated by this blue trajectory marked with arrow. The trajectory is able to go back, to transiently go back, go beyond the basin of attraction of this point. But once the inhibition is, the excitation is removed, it goes back. So that does not spike. It like starts initiating a spike, but it does not. The spike does not materialize. It cannot. But okay, for some intermediate values of slope, there is a spike. For larger values, which we see on the right panel, so this trajectory marked with star, it's also on the right panel. It also spikes, but again, for large values of slope, it won't spike because the removing of excitation it occurs at the moment when it is again like tracked back in the basin of attraction of the fixed point. So I had a movie that of course I don't have time for the details, yes, but there's a theorem on that, and in this theorem you only need to care that actually the amplitude A, it cannot be too large, because if it is too large, then your neuron may undergo this saddle node on invariant cycle or Hopf bifurcation, yes, and we need to make sure that we are not in this range of parameter set. So, but with this constraint, indeed, there is no spiking for large or small slope. But when the amplitude does not exceed this level, but it's high enough, then there is some set of slope values for which the solution blow up in finite time. So let me maybe display the movie. I hope you see it. Yes. So what you will see on the movie, you will see this recording, yes, of this some numerical experiment. You will always see the two nucleons corresponding to 0 input level with actually the vertical W nucleon. So this corresponds to C0. And you will also see the black curve that will correspond to the V nucleon corresponding to the current input level. And you will also see the yellow curve, which is the trajectory. Maybe I will display this movie. Yes. You will also see the yellow trajectory. That is the current trajectory. So the current state of the neuron, yes, with this black arrow being actually the current endpoint of this trajectory. Yes, so what we've seen here, it was that when a slope is actually very small, the neuron, it actually follows the nucleons, follows the fixed point. So we slightly increase the slope, but still there is no spiking, yes. And just after transition, yes, we were lucky enough, yes, the spike was fired, yes, it was just enough time. Here, it was like let's say the safe situation, yes. We were really, when we look at this, we see that we were there was enough time to actually start initiating the spike and also to complete this spike, because before this black curve again went down and trapped our trajectory. Yes, and this is just before the transition to non-spiking. Yes, so here the spike is too large. The slope is too large, and for very large slope, the input is actually very brief. And what happens? Okay, so I think this is the end of the movie. And I think I'm completely running out of time, so I think I'm not going to mention this further work unless you will ask me. Of course, I will be happy to say something about that. So thank you, and I'm sorry for when I was trying to practice this talk, it took me like 45 minutes, but I was longer. I apologize.
No worries. Thank you so much for such a wonderful talk. So please feel free to ask Justyna any question if you have.
I hope I didn't bother you too much with some technicalities, although I'm afraid I did.
Can I ask a question?
Yes.
Thank you for a nice talk. I have a question about the slope detection. So in your study, you assumed like smooth curve as the input, but what if the input is noisy? That if you look at the input locally, the slope is very steep.
Mm-hmm.
But if you look at globally, it's still moderate enough. So does it have the noise cancellation kind of?
Okay, so yes, so in our study, the input was purely deterministic. Yes, it was well, maybe not smooth, but a continuous function without any noise.
Right.
And now I guess you ask what happens if we have some component, so we add some noise here. Yes, so we didn't include the noise, but well, I think that these both properties, they're quite robust. So I think that unless if this noise level is small, I think that this phenomena is going to persist. But yes, it can be, of course, a bit different study if we consider different values of noise. Actually, if I can I can show you the pictures from the paper that was a sort of inspiration for us, because our future work is going to concentrate on showing the other two properties, the coincidence detection and phase locking. And
before you do that, can I add something on the question?
Yes, yes.
I think it's an interesting question of vocabulary, because I mean we didn't choose the name of slope detection, but what we find is that it's not only the slope that matters. And what you say is that if we put noise, then we have very large slopes in the sense of the derivative, even infinite. No, I mean, if it's white noise, we have infinite derivative, etc. And so what we see really is that it's not only the slope that matters, but it's also the duration during which you maintain a slope, and also what happens after the slope. And so the whole thing that we say is that when your input is I mean, the basis of the proof doesn't have to do a lot with the tense. What it's telling you is that, and what you see in the movie, is that the input has to move fast enough so that the neuron so that the neuron becomes very far away from the current fixed point, and so that it's so far that it starts a spike. Okay, but because of the type of the tent that we have, if the takeoff is very fast, then the shutdown of the input is also very fast because we have the same slope. And so that's why we find this kind of balance where if it's too slow, you just stay near the fixed point because it's moving too slowly. But if it's too fast, your point on the phase plane is in the middle of nowhere, so in the region of spiking, but you collapse fast enough so that you catch it back up before it has time to go far away. Now, if you put noise, these little kind of very large slopes will not matter too much. And that's because we integrate a differential equation with noise. So your solution will kind of follow some kind of inputs, like at a lower frequency, lower frequencies. And in fact, it's going to be these lower frequencies that will be more important. And I guess the question of what are the frequencies that are important really, I don't know, but I think it's an interesting question. And it doesn't have to do only with slope. I think that the terminology of slope detection is a little confusing in that case. We didn't choose it, but it's.
Yes, and as Joanna said, it's not that the 10th input is necessary. We just wanted to have analytical, completely rigorous proof, and the form of 10th input makes it feasible, yes, to write formulas to make some estimations. So, and yes, as it was mentioned and as it depicted here, yeah.
If we had something like that, I guess, Justyna, you agree with me, but if we had something like that, we would have no spike, and here we would have spike, and
yes.
here we have no spike. So,
yes.
So there is something behind it that is more than slope in the sense of the derivative.
Yes, and also I also said that this the slope beta, it is also directly connected with the total input received by the neuron. Yes, so if your input is not exactly like that, but if there is a bit noisy, then the total input received by the neuron does not change that much. So, okay.
You have 2 more questions in the chat. Maybe Gaëtan, you can ask the question. You are panelist now. You can speak, I think.
Okay, I see.
Can you hear me?
Yes.
Okay. I was just wondering if when you did the bifurcation on the slope detection, did you look at the case when the integral beneath the tent is taken as constant? Because for me, it's like the total input that is integrated, so it's an important quantity. And here you just look at the amplitude, so A, if I remember well, and the slope beta, but you don't look along the line where A square over beta is taken as constant. I'm not sure. Because if I look at your examples below, it's kind of logical that the third one does not spike because there is really slow integrated input. Because there is when you look at the area under the curve, it's logical it doesn't spike in a way. I mean,
yeah, that's the reason why it doesn't spike.
Okay, but then it's not really a slope detection. It's just the integrated input is lower than in the previous case.
And that's how people define it. If you change the amplitude and the slope, you're doing something else. Here, when you're changing just the slope, you don't want also to keep, you want to change the slope, but keep the duration constant, for instance. That's what you would like to do. And so finish at
No,
a high.
I would like to change the slope, but to keep the area under the curve constant.
Yeah, we could.
That would be the most logical way for me to, when you talk about slope detection, because here you have two mixed effects, which are the total integrated input and the slope, but they are mixed in a way.
They are always mixed, I think.
Yeah, because so in this definition of the slope detection, so it's not the thing that we defined. It was also like assumed that you consider some fixed amplitude, yes, and for some fixed amplitude, actually when slope is in some immediate or in some medium range, it can maybe it can spike. So like I think like the fixed amplitude, I think it's part of the definition of the slope detection, that you keep the amplitude but you change the slope. But yes, of course it is connected with the total inputs injected to the neuron, and so from this point of view it's maybe not that surprising, yes, that it happens.
Yeah, so the proof, in fact, it says that for a very large slope, the fixed point stays arbitrarily close to the original position. And so because the fixed point is stable, you will be in the attraction bassin of the fixed point at the end of the stimulus. So that's what we use for the proof. And for the large slope, we say it's so slow that in fact it's tracking the fixed point, the instantaneous fixed point, as the null line moves. So this is how we prove the two endpoints. And then the real trick is to understand why would you spike in the middle. That's really what is interesting in the proof and not completely obvious.
Yes. So like showing not spiking for small slopes and showing no spiking for very large slopes was not that hard at showing that actually you spike for some middle values of slopes, yes, because non-spiking for small slopes and non-spiking for large slopes does not mean that you will spike does not immediately imply that you will spike for some immediate values of slopes. Okay, and
thanks.
And there is some other question, I think, on the chat. Yes, if I could say something about the phase locking. So personally, I like such phenomena as phase locking, but actually it seems to be hard for us to address this question properly. And we keep thinking about it since some time. So maybe let me just say how it is, let's say, addressed in the paper of Meng, Hugot, and Rinsel, in which they consider these type 3 excitability properties, yes, that we mentioned, as well as coincidence detection and phase locking for some Rothman-Manis model. So this is a model that is actually similar to Hodgkin-Huxley model, and it can be also used to, for example, model some auditory system phenomena, like the cells, the neurons that are important in actually processing the auditory stimulus. But okay, they also, to be for completeness, yes, I also mentioned that they also consider some planar reductions of this model. But so they actually considered for both coincidence detection and phase locking. They considered this model with the input of this form, as I have it here at the bottom, which is not like tend, but which is like rectified sinus sign. So we take the positive part of sine, yes, and it is sustained input, yes. So it has there is a part of this sign when it is non-zero, then some zero part that normally could correspond to the negative part of sign, then positive part of sign again, and so on. And so they consider a stimulus which is actually composed of two such signs, but the one is shifted with some there is some delta p phase shift. So this can correspond to the actually tone that one ear is receiving and then the other ear received this like let's say this shifted tone. Yes, and they also included some noise. So but they also considered zero noise level, but also non-zero input level. So what they actually addressed here as phase locking is the fact that when they compared their model in phasic range of parameters with the models with the model that was in tonic case, they indicated whether the spike was fired and at which phases of the forcing period it was fired. So when they make like histogram of this value, so like let's say actually it was, I think, the histogram of firing they noticed that this histogram, this distribution of firing phases for the phasic case was actually, it was really narrow when compared with the tonic case. Yes, so unless this shift delta p was about 0.5, when actually these two signs, they become like completely disjoint. Yes, so but otherwise this distribution was really narrowed compared to the distribution obtained for the tonic case. So it means that like we can call it like precision of phase locking, so that not only the neuron, okay, like some special conditions to actually fire, but it also, when it fires on some, let's say, prescribed bounded range of phases. And we would like to also to somehow in the future address this issue in our in this planar hybrid model. So I yes, for the time being, unfortunately, we cannot say more about phase locking, but we will see. Maybe it will demonstrate in our model as well.
Do we have any more questions for Justyna? All right, then we will wrap up here for today. I'd like to thank our speaker, Justyna, again, and everyone for the participation. I will see you all hopefully next week. Take care, guys.
Thank you. Bye-bye.
See you. Bye. Thank you.